Well, again, we want to thank you today for joining us for our next Force Leaders event. Today we have Brian Peters and Jeff White, who will be presenting on all the questions you might have about specifications. And then, of course, we have Keith Skidmore on board to help in our Q&A. We appreciate you taking the time to spend with us today. We hope that the details that we provide you will give you all the information that you need about kind of demystifying specifications, data sheets, product differentiators, and things that are important when making a decision about choosing your sensors and technologies and instrumentation. This event is recorded. We will be providing the recording to everyone that has registered to attend, and also be posting that on our YouTube channel. There is a chat feature, so please use that for any questions, and we will try to address those when we get to our Q&A. Again, thanks for joining us today. Let's kick things off. Brian, are you ready?
Yeah, absolutely.
All right.
All right. Well, thanks, everybody. It's a pleasure to get to speak with you all this morning or afternoon or evening, depending on where you are located. Appreciate you taking time out of your day. So these are the topics we're going to touch on today. Specifications obviously cover a wide range of information, but we're going to be going over basics and then tune it in a little bit more to force measurement. Also be covering how to interpret data sheets, what's on there, areas to look at and understand. Do a deeper dive on product specs for load cells, specifically around some of the performance-related specifications. And then we'll do a light touch on instrumentation. Instrumentation is a little bit of a different animal than just a sensor itself, but we'll arm you guys and gals with some information to make the right decision and choice in that arena as well. We'll cover a couple specialty sensor products where, depending on the application, you might need to think differently about specifications to either ask or confirm or share from an application standpoint. So we make sure we get things designed appropriately. And then also cover a few applications that drive specific considerations on specs. Then some general tips at the end, and then FAQ and open Q&A, of course. So, all right, Jamie? Specification basics. I think, Jeff, you're going to kick us off here.
Yeah, thanks, Jamie. Thanks, Brian. Specification definition rolls right off the tongue. So today we are going to define specifications and make sense of what is on an interface data sheet. We'll go over the specifications, characteristics, features, and qualities of our products, mainly load cells. We'll touch on multi-axis, instrumentation, accessories, and some of our specialty products with specifications that stand out when compared to other products. This will be important because what we talk about today applies to just about all of the products and answers the questions to the most basic yet most important question: which sensor, instrument, or accessory should I choose? Not only do we publish specifications, we also hold internally a list of specifications that all of our products must meet before we box it up, put it in stock, and ship it to you. Next slide. So everything that we talk about can fall into one of these four basic categories of specifications. Functional kind of describes a product's intended purpose and capabilities. Technical describes product's electrical and mechanical characteristics. Performance, these are the measurables and really what we're talking about today. It describes what kind of accuracy you can expect from the load cell, usually expressed as maximum error. Design is the look and feel and makes sure the deliverable product can hit the above specifications. So functional specifications. So this is often the first consideration when making a selection. This covers what it does and how it does it. Questions to ask yourself: do I need something that can take a high axial force or detect a finite torque measurement, or an enclosure to house an instrument? Some of this will be covered in the features and benefits, and the results will be expressed in the numbers of the specifications. Slide. Technical specifications. Much of the technical specifications are covered in the mechanical specifications. This provides details such as material, which will most likely be defined by the environment, physical dimensions. Will this fit into my application? Some of the performance criteria, capacity, not only if the cell is calibrated in one or both directions, but if it performs in one or both directions. Next slide. So performance specifications. So this is the meat and potatoes of the data sheet. When you dig into the performance specifications and compare the numbers from one model to the next, only then can you make an informed decision on which load cell is best for your application. Many look alike, but if you need to drive down your uncertainty, this is what is important. We'll talk about speed, accuracy, capacity, and reliability. We'll also look at a range of capacity the sensor performs the best. Load cells don't always perform the same from 0 to full scale. If you have a desired measurement goal, the performance specifications are absolutely critical in making a decision. While I'm sure every manufacturer would gladly sell their top-of-the-line product every time, a standard product may very well meet or exceed your requirements. Design specifications. So design specifications include the dimensions, cable exit, cover placement, and other attributes that make up the look and feel of the product. Many of these are taken for granted, but if overlooked, can cause unnecessary and unavoidable problems in the field. You can see the 2D drawing, also available in 3D, of our very popular SSM load cell to the right. By following the designed specifications, we can ensure that what is delivered is what you expect to see. So Brian, I'll pass it to you to dig a little deeper.
All right, thanks, Jeff. Okay, if you look at one of our data sheets, you're going to have different categories listed on there. Product models, there'll be specifications, information section, there'll be dimensional section, options, different connector types that you can choose from, and then accessories. So this section right now, we're going to be talking more specifically about the, as Jeff said, the meat and potatoes, the specification section. So next slide, there we go. So again, it starts off with the model. What is the load cell model? What are the available capacities for that model? And then also measurement units. Are you looking for pounds force? Are you looking for kilonewton? And then we get into the accuracy specs. It will be multiple specific aspects that fall under the accuracy umbrella, which I'll be touching on here shortly. And then we have the temperature in terms of what it can tolerate, how it reacts to temperature, and then of course electrical and mechanical properties for the sensor. So next slide.
That's kind of
All right. All right, so looking at accuracy here, under the accuracy section, these are the common specifications you're going to see on interface data sheets as well as most other sensors. So nonlinearity, hysteresis, static error band, non-repeatability, creep, side load sensitivity, eccentric load sensitivity. Now, those last two you may not see on most other product data sheets, and you'll see it on all of our moment compensated load cell products. So, all right, let's go to nonlinearity. So nonlinearity, in a perfect world, a sensor is perfectly linear. So as you increase force, the signal tracks perfectly linear. Despite our best efforts, not every sensor is perfectly linear. So there'll be a nonlinearity spec that just captures how much does it deviate off that best fit straight, off the straight line theoretical ideal environment. And units on that are going to be percent of full scale. Next slide. All right, hysteresis. So hysteresis is the difference in output on a descending load versus what the load cell produced on the ascending, or the sensor produced on the ascending. So what that means is if you increase load and you are increasing up to full scale, and then you hit one of the same points that you took on the ascending side, and you revisit that point as you're releasing the load, that output might not be exactly the same it was on the ascending side. So that's going to be defined as a hysteresis value. And that's going to be percent of full scale as well. So you can understand too, maybe that doesn't apply for my application if I'm only doing a single load and I want to track the force that's being applied through that test, right? So there's hysteresis. Next one. All right, static error band. This is something not all sensor data sheets have. A lot of them do. This is a good way to look at kind of a summary on performance for the load cell, and that's because it takes into account the nonlinearity on the ascending side, the hysteresis value on descending, as well as a non-return to zero. So it's actually as stated, an error band that encompasses all the deviation of output for that load cell in a test or in a calibration. And the SEB output is the best fit straight line within that error band. And we specify that SEB output on many of our calibration certificates. So again, if you're looking for an output that takes into account linearity, hysteresis, and non-return to zero, that would be the best output to use from a instrumentation calibration standpoint. So non-repeatability. Non-repeatability is essentially, as it says, how often or how much will a sensor deviate if you test it over and over again. Now, the key to note here is that's in identical loading and environmental conditions. So everything is being held constant. Typically, it would even be in the same installation. So you can imagine in the real world, you can't take this specification and assume that the sensor is going to be repeatable from test to test based on this specification. So this is a specification for stability. In particular, this is something that you're really looking for from a calibration grade load cell as well. So your reference standard, you want to have really good non-repeatability so that that sensor hits the same points every time, right? Next slide. Creep. So creep is a physical phenomenon that all mechanical and physical elements respond to. And essentially, it's a very slight change in deflection over time, even when you're applying the same load. So as far as a sensor is concerned, the creep spec would quantify how much the signal might deviate as you maintain that constant load. Now, the goal is that in the case of our load cells, which are foil-based strain gauge Wheatstone bridge elements, that the gauges are responding identically from a creep standpoint as whatever material they're bonded to, right? The key takeaway here is a couple. One is that it's a logarithmic effect. So most of the influence happens relatively early and then it decays over time. The interesting thing too is that it's easy to quantify typically in that it will respond or pull out of the system in the same way that it is introduced. So in other words, if you are doing a long duration test and you want to be able to get an idea of how much potential creep error might have been introduced to the system, as soon as you remove that load, you'll see a non-zero signal, and that signal will eventually decay back to zero in a mirrored behavior as the creep was introduced. So the other thing to note too, that pay close attention to the units. It's a percent of applied load over a time interval, and a lot of manufacturers won't always specify the same time interval. So even though you see two specs, they may look to be assumed to be similar. You got to take note of the time aspect. So Interface actually has a more aggressive 20-minute interval that we spec our load cells to. Next slide. Eccentric and side load sensitivity. So you'll find this on many of our products, or actually all of our products that are moment compensated. In particular, our low profile pancake load cells, or those of you familiar with Interface products, are 1000, 1100, 1200, 1600, 1800, 5200. We'll specify how sensitive the sensor is to non-primary axis loading, right? So for an axial load cell, it would be bending moments, it would be a torsional load perhaps, or a side load. So side load perpendicular and eccentric, anything not perfectly concentric with the axis. So these are in percent or percent per inch. So pay close attention to that. And again, as Jeff alluded, we have a lot of specs internal and some that are on the data sheet that the units are tested to, right? And this is certainly one of them. In fact, most specifications on an Interface data sheet, every single unit is tested to. Others are design related, and we've got full confidence there. But every single load cell from Interface that has an eccentric or side load spec on the data sheet, it's tested to that. Next slide. All right, temperature. We're gonna do a little bit more of a zoom in here on temperature. It's important. Hopefully want everyone to come away today having a better understanding of how temperature affects load cells, and would be true for probably pressure sensors and other foil-based sensors, or strain gauge-based sensors, I should say. But there's a couple parameters: one, operating range; two, compensated range; and then the effect on zero and effect on span. So next slide. Operating range is as expected. This is the temperature range that the sensor can be operated in without any damage or anything that would be long term. Now, pay attention that just because it has an operating range for that, you may see some error influence as the load cell or sensor is subjected to varying temperatures within that range. And so that's the next part here. So the next slide. Compensated range. So compensated range is the temperature range that we are guaranteeing the sensor to maintain temperature-related performance specs within. So you'll see in this example, the table there, operating range, -65 to 200, and we have a compensated range of 15 to 115. So the other thing to note too is a lot of most interface products are a cold to hot compensated range. Competitors often will do room to hot. But the cold to hot is definitely flatter. And again, within that compensated range, it's going to maintain certain specifications. So on the next slide. So within that compensated range, we're going to maintain that the sensor will hit certain specs with regards to effect on zero and effect on output. So temperature is going to affect a load cell in two ways. One, it's going to affect what happens with the zero balance. These are ratiometric bridges, and ideally they maintain a zero value. But as temperature changes, the zero value might drift a little bit. So we specify how much it'll change, and it's a change per degree F. So it's a percent per change in temperature. And then the other aspect to keep in mind is the effect on output. So meaning how much signal are you going to have from that sensor, or how much change to your output will you see on the sensor through a temperature change. So you'll see over on the right there that the compensated range is essentially, you can think of it as a flattening of the curve within that range. And most of the time we're around 100-degree window that we compensate, tighten in for. Load cells certainly can be used outside the compensated range. It's not going to suddenly have a fall off a cliff in terms of what's going to happen to the signal or the zero balance, but you can imagine that's going to start to deviate, outside, of course, the specified range as soon as you get out of that stated value there. Important notes, though, and we're going to touch on this a little bit more too, is it's characterizable and it's repeatable. So how the sensor responds to temperature will be the same, and each unit's going to be a little bit different. So we test every single load cell from a zero balance standpoint to make sure that it meets the temperature requirements. And even with the adjustments, we actually run them back through and do verification. That's another step that we do that a lot of competitors don't do. But it is important to note that temperature influence is repeatable. Okay, so there's a lot of characterization and testing that can be done to see how a sensor responds, and then adjust your test data accordingly. So next slide. All right, on the electrical side, there's usually a few things listed on the data sheet there. Rated output, so how much signal are you going to have at capacity? And that is millivolt per volt for most of our sensors. If that was amplified, it would have a voltage or milliamp rating there. Excitation voltage, this is how much voltage the sensor it can tolerate. We list a max value. Most sensors you're going to want to use about a 5 or a 10 volt. Running more voltage, not necessarily better. So the bridge resistance, most of our sensors are going to be 350 ohm. Some vary. It's a good thing to note if you're going to try to use a single instrument to run multiple sensors. You got to make sure that it's got the amperage to be able to push all those sensors. And zero balance, how much is the zero going to deviate from unit to unit, right? So we maintain most sensors that it's going to be within 1% of the rated output. Insulation resistance is a measurement of isolation of the bridge to the load cell material, and that'll vary also depending on the product. Next slide. On the mechanical side, so mechanical section is going to cover safe overload, how much force above capacity can it tolerate without permanent damage, the deflection, so that's going to be the specification of how much the load cell will move. There'll be a live end and a dead end, but how much total deflection, again, at the rated output or capacity if it's a full-scale cal. Most load cells are going to be very, very small deflection. You can see 0.001 inch in this case. Stiffer is generally better, but some lower capacity, some minis that we offer due to the design, get desired output, etc. You may have more deflection, so it's something to keep in mind depending on what your test requirements are. We'll list out if there's an optional base for that. So this is an LP, a snippet from an LP. So we have a B101 kit. If you want metric thread, you would put the M on there. Natural frequency, again, this is correlating to multiple capacities within the a single model family. But that's good to note too if you start getting into dynamic or high cycle testing to keep in mind in terms of how stiff the sensor is. And then weight, calibration. Not all sensors get the same calibration, so you'll want to note, do you have a tension or compression? You can typically use sensors in opposite modes. They should be pretty symmetric, but again, if you want to have that specific mode cal data, you can always ask for it if it isn't standard for that model. And then material. All right, Jeff, data sheets.
All right, let's put on our reading glasses. So now that we have an understanding of the specifications, let's dive into the data sheet. We're going to cover what information is included in a data sheet, what information is useful, why it's important, and why should this be considered when making an informed buying decision. Let's decode the data sheet. So listed here is what we include in just about every data sheet. Features and benefits is a quick snapshot of what we believe may lead to you choosing or not choosing a specific model. Drawings and dimensions will quickly know if this physically fits into your application. Specifications, this is what the presentation is all about, and will certainly guide us into making the best selection. Model is important to note. I will bring it up again, but many times one capacity multiple capacities will be listed within the same model. The capacity, how much force can the sensor measure? Options and accessories, so certainly offer more than just sensors. We have cables, bases, connectors, and so on. So first, features and benefits. Capacity range. So be sure that we're looking at a model in which the force value you need to measure falls within. We will talk about how to size your load cell appropriately. There will be always a trade-off between capacity and resolution. We need to be sure that we size the load cell appropriately to make sure we don't overload the cell, but be sure that we can also measure the smallest increase that you need to see. Performance. Brian spoke of many of the performance specifications of which to consider. Be sure to focus on what is important to you and your application. If you are interested, or maybe you're not interested in taking any descending loads, therefore the hysteresis may not be important to you. Creep may or may not be important to you depending on how you are measuring the forces related to your application. Once you start considering eccentric and side loads, you may realize that you're interested or not interested in those values, and maybe a multi-axis load cell is the direction we need to start going down. Are thermal specifications important to you? Might you want to expand the zero compensation range, or even adjust, would you want to expand the zero compensation range, or adjust the span range as well? Next is output. We offer a 4 millivolt per volt output on many load cells, making it very attractive to some customers, but note that when you get into fatigue applications, the output will be cut in half. Speaking of fatigue, the number of cycles. This is a detail that is sometimes not always offered up at the beginning of the search for the best load cell, but always important to the success of your measurement. The calibration method, is it going to be tension and compression? Calibration adapter. We offer load cells with integrated cal adapters and therefore able to meet much tighter performance specs. So the model will determine the flexure. The flexure is the unfinished load cell. And a lot of times we will put this into stock and can be finished into a number of products, depending on the capacity, options, and accessories that you choose. We offer just about every load cell in imperial and metric. If you don't see it, ask for it. One little bit of information that might be useful is if you initially oversize or undersize a load cell, you may be able to swap that out with a higher or lower capacity without changing any mounting hardware, just due to the way that we have multiple capacities per one model. Next slide. So drawing in dimensions, you might decide that a low profile is too wide or a column is too tall. Right off the bat, you can decide which model you might want to go to based on the dimensions. We had an interesting application where we decided that a flange mount low profile load cell seemed to be the best fit. It was quoted, and later on down during our discussions, the customer decided to let us know the number of cycles. Now, while the load cell itself would hold up to hundreds of thousands of cycles, the fasteners would not. So had the customer moved forward with this model, they would have needed to change out fasteners every couple 100,000 cycles. It could have caused issues to their data, would also add labor and downtime. So just some important considerations. Slide. So notice here, as I mentioned before, 6 different capacities fall into one model size. So it's just important, it could be confusing if you're looking at the data sheet for the first time if you notice a number of capacities within the same model number. So just important to note. Next is capacity. So this is often the first question when asked when choosing a load cell. Relatively straightforward, but definitely critical to the success of the application. Personal rule of thumb is offer as much capacity as you can while achieving the necessary resolution, then consider the cost. If you do this, your load cell may survive an overload that a smaller capacity cell would not. You can kind of see how we graph it here. You start with the working range, which you want to normally stay within. The overload range, you can certainly go into the yellow there. You don't want to live in the yellow, but once you get into the red, you might damage the load cell so that it will no longer perform. And once you go past that, you might have a load cell that breaks in half. Options and accessories. So last but not least, bases are very important. A base is needed to ensure that the published specifications are met. While you can provide your own base, we are more than happy to do it for you. Connector protectors make sense for high capacity load cells. I'd hate to ruin a whole sensor by just damaging a connector. Custom calibrations. Typically, calibration is 5 points up, 1 point down. At some other models, it might just be 0 and at full scale. While this is fine for most applications, we're happy to kind of focus in on your area of interest. We can ignore, by doing this, we can ignore some of the errors that are taken into consideration when coming up an uncertain budget if this is done. Multiple bridges, very popular option that we quote pretty often. It could be for redundancy, or if you're sending your information out to multiple data acquisitions. Dual or vented diaphragm, we will offer these options based on the environment. Are we keeping out water, or are we going into high pressure or vacuum environment? Special temperature range. We can widen the compensated range at 0. We can even do some span adjustment. Cable length, it's always a good thing to note how far the load cell will be from the instrument. We can make special cable lengths and a lot of times offer sense. So that would be your 6 wire, which will account for a potential drop in excitation voltage if you're running over a typical length. And then TEDs, if you need to swap in load cells in and out frequently, this will allow for easy plug and play. Detailing product specs. So we'll go over a number of use cases here. The first one is high performance. So the 1800 Platinum Standard, this is our top of the line load cell. It offers ultimate precision and the tightest specifications on any interface data sheet. Of course, it can be used in either tension or compression. It includes an E74 calibration. Our production process ensures that it will be very repeatable, hit the same points over and over again. It's about 2 times as good as the standard product. You'll notice the bridge resistance. Normally 350 ohms is standard. This is 700 ohms. This is because we use 16 strain gauges, twice as much as a normal load cell, and gives us the enhanced moment sensitivity. And it is as good as it gets regarding temperature deviation during testing. We have some very durable load cells as well. So there are 1,000 low profile fatigue rated load cell. It is one beefy load cell that is good for 100 million fully reversed cycles, tension and compression through 0. So as long as this is not overloaded, we have yet to see 1,000 series load cell come back due to fatigue failure. Low deflection means that it is very stiff and it is good for dynamic applications. As this is fatigue rated, we will only use half the cell's working capacity. Therefore, the overload protection is tremendous. A wide range of temperature compensation as well. The ATQ is our wireless rotary torque device capable of providing highly accurate readings down to 0.05%. We at Interface realizes a highly competitive market and must offer a high performing sensor. One specification that stands out is a dimensional spec. The ATQ is a large axial gap up to 5 millimeters and radially typically 12 millimeters between the rotor and stator. This makes it highly unlikely that the rotor will make contact with the stator and do something you don't want it to do. It offers a relatively high IP rating for a wireless product, IP65, 200% safe overload protection, a wide range of operating in compensated temperature to perform in, and up to 20,000 RPM.
Yeah, so there's other rotary torque measurement options. We offer quite a few that have shafts. But again, sorry if you can go back real quick. From a durability standpoint, this lends itself really well. These are some of the specifications that you'd want to zoom in on when you're selecting a sensor for durable torque testing. Essentially, this is a separate rotor stator assembly, so there's no rotating parts to wear out, no bearings to wear out. It also has pretty high overload, which I think we forgot to put in. Oh yeah, there's 200%. So much higher safe overload in terms of being able to handle a shock or some inertial issues, which sometimes pop up in rotary torque. So, all right.
All right, environmental durability. So we'll highlight the WMC mini load cell. So it boasts an environmental durability great for industrial applications, available in capacities from 5 to 500 pounds. It is a stainless steel, welded steel construction, available in tension and compression. It is one of a few products that can be fully submersed. A lot of the times we will ask you how deep and for how long and what is the medium, and then we will design the load cell appropriately. Next slide. So now we get into the small form factor. So the SMTM Micro S-Type Mini is a very popular model that can fit into some of the smallest medical test and measurement and industrial applications we encounter. You can see the size there. Another one to note is the overload protection, 1,000% of the capacity, while still offering a 2 millivolt per volt output, and boasts a very robust temperature spec. Slide. So these are the start of our multi-axis cells and get much more complex moving forward. The sensor type drives the axis capacities. So you will see that we have sensors with a very high axial force with the ability to detect very fine torque measurements. We also have high torque with very fine axial force measurements.
Yeah, some of that's going to be a function of how the sensor originally started. So the unit on the left out of the 1500 that started as an axial load cell, We added some additional bridge on there for torsional measurement, whereas the one on the right, that started as a torque cell. So it's going to probably have, for similar capacities, it's going to be shifted much higher on the torque side with maybe less sensitivity in the axial mode, for example. So it's just good to pay attention to, again, the how the different capacities in the multi-axis line up. And we usually have a solution that'll get what's needed. So don't hesitate to reach out and ask on that.
So more multi-axis, these get a little bit more complex. We speak a lot about how our low profile load cells have the ability to ignore off-axis and side loads, but what if those forces are important to you? We offer a full line of 3A and 6A load cells. So depending on which load cell you choose, it will also drive the instrument that you need. So the 3A offers your FX, FY, FZ. It is very symmetrical and has discrete channel output, where the 6A will deliver a composite signal. You can see all your axial forces as well as all of your moments. And this needs a matrix to decipher what direction and force value the force is coming from.
Yeah, so in terms of specs, right, it's good to note, okay, how symmetric are the multi-axes that you're looking for? 3 axes, they're discrete, meaning you can think of it as 3 individual axes or 3 individual sensors, all giving you isolated output for each axis. Whereas the 6 axis, and as Jeff mentioned, outputs 6 channels worth of data, and thus the instrumentation is really important to be able to calculate the individual axis specific output. So that's how these load cells are calibrated, and they're anticipated to be used with that. And now on the earlier slide where we're talking about varying levels of capacities, we do have different offerings on the 6 axis, for example, where if you do need high moment, if it's a wind balance type application or something where you're going to have a big overhang, or from where your test article is, for example, or where the load is introduced, we've got different solutions to accommodate that. So it might drive a different form factor, it might drive a different version, but pay attention to, again, the specific capacity ratings for the different axes. All right, instrumentation. So as I started off, instrumentation is a pretty wide category. And so the takeaway here that I hope to deliver on is just understanding which specs to zoom in on for instrumentation and things that may have caught customers out in the past. So instrumentation in general covers a wide range of products and solutions. It could be panel meters, displays, signal conditioners, data loggers, handhelds. And they also may vary in how many channels they support or what types of channels they support, especially with regards to the signal types. So what kind of inputs can they tolerate? What are the ranges that they can tolerate for those inputs? And then what kind of excitation can they provide, right? On the many of these have throughputs or outputs. So then it'd be a function of understanding and looking at the specifications around the output types. Is it a straight through? Is it scalable? Is it not scalable? Does it have the analog or digital output specifically that you're looking for? Then there's the performance specs. Those are pretty straightforward. Performance specs will vary a little bit from unit to unit in terms of what's listed or what's tested. Then the environmental, does it have adequate IP? Is it splashdown rated? Does it need an enclosure? And then the software compatibility. So again, these can tie often to different software, whether it's to capture the data or to further enhance the measurement capability of that sensor or the instrument, excuse me. Next slide. So as I mentioned, there's a lot of things to keep in mind. So instead of just zooming in on the specification portion of the data sheet for these types of devices, you want to be looking more maybe on the features and benefits. That's where we're going to go through and highlight what it's capable of, what its functionality is, to make sure that it's going to meet your specific measurement requirements. So again, pay close attention to input, the internal and output specs. So we need to think of it in terms of what can it take coming in, what is it capable of internally, and then what can it do on the output side if you need that signal to move forward. And as I mentioned, Specifications can vary. Next. So let's consider a use case of high speed. So let's say you're going to have a relatively high speed test. You want to be able to make sure that you get all the data you're looking for. Well, obviously, you're going to want to zoom in on sample rate. You're going to want to look at the filtering limitations. Sometimes you'll need to either filter noise out or not. If you do filter noise, how does that impact your ability to capture peak dynamic events? What are the A to D limitations? So I mentioned that there's internal specifications, right? So what is the device capable of in terms of converting the analog signal to digital? Digital meaning the display, or digital maybe the output. Pay close attention to that. What's the speed of that? And then if you're relying on the display, what are the limitations of the ability to refresh or to keep up, right? And then also the outputs. Many of our signal conditioners, or not many, but some, I should say, are capable of straight pass-throughs. So they'll take that analog signal, they'll run it right through the device, and then you have basically a non-filtered pure signal on the outside to take onto your data ACK or somewhere else. Sometimes there's limitations there in terms of what the pass-through is. Sometimes there's not. So pay close attention to that. And then peak capture. You're going to be able to capture that dynamic event, whether it be either on the display or with your software. So a couple models on the high-speed arena, 9325. That's a portable handheld. It happens to be almost 2.5 kilohertz, 500,000 internal counts, and still 24-bit. So a good high-speed option there. 9330, almost 4 kilohertz sample. Has peak capture as well, 24-bit, so high resolution. It logs to the SD card at 1 kilohertz. So that's something, again, an example of making sure that you have alignment in terms of what you're looking to do. So if you need to log the data higher than 1 kilohertz, you might need to run it through or pick a different device. BX8, very high speed. That's 48 kilohertz, and that's per channel. These are actually 8-channel devices. 24 bits of high resolution, and you have full selectable filters, input output, and then active output scaling. So you can actually define what you want the output channels to scale to, as well as defining what filtering you want on that. So keep in mind, again, with a high-speed application, make sure the settings are set right and you're actually seeing what you think you are. INF USB, inline USB signal conditioner, 5 kilohertz, 16-bit. The software is also set up to handle quick events. So you can actually configure trigger captures, meaning you start sampling data at a high rate. Once the signal reaches certain thresholds, turn off that data capture at a certain point. So again, works well with the high-speed events or high-speed applications. Next slide. So let's look at now if you need a very accurate, very precise measurement. Well, now you're going to start shifting to looking at internal resolution with priority, perhaps. What's the linearity of the device? How many display digits do you actually get to see on that? Stability, drift, those start to come into the picture. Sense leads is a 6-wire, like Jeff was talking about earlier. That's a huge benefit if you've got long cable runs, for example, to ensure that the signal, or excuse me, the instrumentation is taking into account any signal loss over that long cable run. Software linearization. So this is something that our gold standard software in particular does, where it'll actually take the signal straight through the device, and it will apply a polynomial equation essentially. So now you've essentially removed linearity concerns really from your sensor, because you've been able to now get such a well-defined output curve in your instrumentation. Then there's also, is it internally calibrated? Do you need to have proof? Do you need to have A2LA accredited internal calibration, millivolt per volt cal on that instrument? How much deviation might there be without that? All right, and as far as a couple options, 9840, it's a great go-to, as well as the 4-channel version, the 9840-400. These are 24-bit, very low error, very high display counts, and they do accommodate not only internal 10-point linearization, but can accommodate our gold standard software support, where you can apply any order of magnitude polynomial you want to if you have detailed cal data for that sensor. And then you also get a 16-bit scalable analog output too. If you need to drive control, for example, we use this for our hydraulic load frames or to run into another data ACK. The 9325 handheld, we saw it earlier, it's also very, very precise. 24 bits, actually two parts per million on its linearity, so very good there. And an incredible amount of display counts, so a nice handheld, but yet still high-performing device. If you need a DIN rail or a signal conditioner that's easy to small and easy to mount, our ISG DIN rail happens to be a very nice option in that it has an isolated ground and isolated power supply from the sensor side. Remember, sensors are ratiometric, so you want to try to keep things clean. Also offers good nonlinearity, and it still accommodates a wide input range up to 4.5 millivolt per volt. Remember, I mentioned that earlier. Pay close attention when you're choosing instrumentation that it can accommodate. A lot of interface load cells being 4 millivolt per volt, customers have run into issues because a lot of sensors are only 2 or 3. So because we offer that 4, and if you're using something that's 4, make sure that you've got the ability to take full advantage of the additional signal and use it to full scale. All right, specialty products.
All right. So first one, submersible. We have a couple, multiple submersible products offering the highest degree of ingress protection. So we talked about the WMC Mini, but now introducing the load pin. We will let you define the depth, pressure, and duration to build the sensor appropriately. Also important is to note the media. Are we going into water, salt water, saline, something else? What is the concentration of the media? Right now, there are load pins thousands of meters deep working year after year. And we'll talk a little bit more about load pins later on in the presentation.
Yeah, so you won't always find these specs on the data sheet. So typically when you move to submersible, it'd be good to have that discussion with the application engineer or make sure we're aware. We try to make sure that the quotes include this data, so there's no surprises. But it is good to have that discussion. So there's you can consider a whole nother subset of specifications once you get into submersible.
So overload protection. Lower capacities often have internal mechanical stops offering very high overload protection. So there's a few products to highlight here: the ULC, SMT, which we mentioned before, and the 2101 dual range standard compression only. So the ULC is a very high performing, low capacity, high overload protected. It also offers side load overload protection 5 times the capacity, and is very good at ignoring extraneous loads. The 2101 is the dual range, allows for accurate measurements throughout the test range. 4 to 5 times overload protection on lower capacity load cells, high output for both ranges up to 4 millivolts per volt. And they are both going to be eccentric load and moment compensated. The SMTM we mentioned before can be used in tension and compression. It is micro-sized. It has excellent temperature compensation and is overload protected as well.
Yeah, the ULC reference, that's a half Newton capacity. So again, when you're dealing with very low capacity sensors, the ability to withstand forces above the rated capacity is really important, as Jeff said, especially on the side or non-intended axis, because sometimes just even installing these very low capacity load cells can introduce risk for damage.
So extended temperature. So first, we need to understand how these are affected, but also how we compensate. Temperature is often repeatable and very easy to characterize. So, we are able to remove the error, isolate the temperature. One thing would be good is just to isolate the cell from the temperature if possible. And of course, we are going to compensate the zero balance and span up to a certain capacity if requested.
In general use, yes, we talked about how we can compensate, load cells to different temperature requirements. In actual testing, actual application, of course, you want to try to keep it away from the temperature if you can, right? Get it out of the thermal chamber or isolate it. Oftentimes it introduces more error if you've got to go through some sort of a barrier sleeve or something. So if it is in there, there's things you can do. You can perhaps just test to see how the zero shifts as you sweep through the temperature range for your test without actually applying the load. You can characterize it that way, maybe take it out of your signal. If it's a constant temperature test, but albeit at an extreme, either cold or hot, you can always get the assembly up to that temperature and then tear the load cell. And that's going to remove the zero balance error that was introduced from that temperature change. Now, if it's a changing temperature test, you're going from low to high or cycling, obviously you couldn't do that, but there's sometimes ways that you can start to remove some of these specification errors out of your test measurement. Also to keep in mind here, sorry, Jeff, I'll run with this. There's a cutaway here in this model. And if you look to the left of the cutaway there's a little bit of a pocket. It's important to note how a sensor is actually temperature compensated. So we have specs. We tell you it's going to meet this certain level of temperature change. But you need to make sure that you remember that's assuming a homogeneous temperature profile, right? So if you have a temperature gradient that is localized, maybe it's coming through the load string, for example, which then transfers through the center hub, through the beams, then eventually reaches the outer ring. Very different than if the whole load cell is brought up to temperature, right? So the compensation effectiveness may vary, especially if you have, let's say, a hot or cold airstream right on that little machine pocket. That's where we finish out some of our zero comp, and we do our temp comp. It's usually behind the label on an interface load cell. You'll feel a little hard cover there. If you have localized temperature delta at that versus the rest of the sensor, temp comp may be delayed or it may not even be accurate. So that's just something to keep in mind. You want to try to keep things as consistent as possible. And then you got to factor in too, is there time for everything to get its temperature? Temperature compensation might lag a little bit if there's an extreme change in temperature. It happens very quickly, and the whole load cell hasn't been able to get up to temperature. So those are things to keep in mind. Of course, we can handle custom design if we need to for a more demanding application, but general knowledge of how temp comp works goes a long way to not relying on data that has some error in there. We can cover ranges from negative 100 degrees all the way up to 500 degree F as far as operating ranges. Compensated range, usually around 100 degree flatness of that curve like we showed earlier, and we can shift that cold or hot and kind of move that around depending on your application. But again, remember, we're talking about temp error. Interface delivers very, very strong temperature performance, usually in the neighborhood of again, 0.008 per degree, which isn't a lot. So can't guarantee that from other load cells. Next slide.
So load pins are certainly considered a specialty product. These have more dimensional considerations than the rest of our products. These are pretty much going to be designed to each application. They're all going to be application specific. If you'll notice on the data sheet, we have an integrated questionnaire. It's going to ask you for the length, the radius, your OD, how you want the cable to exit, exactly, we're pretty much replacing a pin in the application with a load sensing element. So they are designed per the application. They are heat treated, old stainless steel, mainly in compression. We can do multiple axes if needed, safe overload protection of 150% or more, and nice little QR code just to get you right to the configurator.
Yeah, so again, another subset of specifications when it comes to load pins. Most of it's going to be around the dimensions. Got to remember how it's important to confirm how you're going to keep the load pin retained axially as well as clocked from a rotational standpoint to ensure that the bridges are lined up with the load. So you can see in the example on the right, this is a standard keeper plate configuration. So that little rectangular plate accomplishes both those tasks, right? We have different configurations depending on the application in terms of being able to accommodate that, but subset, different specifications. Here it's mostly going to be dimensional, physical, some environmental, and also if you need multi-axis, either redundant or biaxial, different groups. Next slide. IPCD. I'll take this one, Jeff. This is an example of a solution that can tolerate some pretty extreme environments. In this case, very high pressure, very high temperature. These are typically rated up to 350 degree from a compensation standpoint, can tolerate 400 degree, and we still maintain pretty good temperature specs, as you see, 0.006, 0.003 across that very wide compensated range. So again, as I said earlier, it's typically around 100 degree spread for comp range. We can certainly achieve custom. But this is also rated for pressure. So while it's primarily downhole, we've certainly sold these to many other applications where there's going to be a pressure influence, and every unit gets tested. So it's going to be a detailed test report that includes all the data to ensure that this meets all these different specifications listed here. You want bases?
I'll take bases. So bases may not seem important, but probably the most important thing to consider is that a base is needed to hit our published performance specifications. So we heat treat them. They are high strength, 0.002 of an inch flat in any 2 points measured. Many different models per the model of the load cell. Always recommended, not necessary, but always recommended in order to hit that performance spec.
All right, applications. So we'll touch on a few applications that have unique requirements when it comes to what specifications to be looking at. So.
And before we jump to that, Brian, can you answer a couple of questions that came in through the chat? And I think some of this was covered. Can you calibrate a load cell at 500, 0 and span?
Good question.
Assuming the application is up to 500?
Yeah, so good question. So like we talked about, where you can do some characterization, yes, we can offer span test data at elevated or cold temperatures. We have some limits in our hardware here, how cold we can go and how hot we can go, but absolutely, especially the IPCD that you all saw, that is absolutely tested at load at temperature as well. And when it's pressure tested, we also do pressure and temp sweeps to ensure that it meets the combined loading conditions. So. But yeah, if you're talking even a regular load cell and you want to, you have a high temp, let's say test, and you want to know how does that load cell perform, we can absolutely do that testing. However, I'm going to touch on this in a little bit. That's the component level performance. As soon as you put that in assembly, every single mechanical joint may respond differently. So be careful that you're not trying to compensate for something where you're actually introducing more error now, because your total system is going to perform differently.
And just one other question, and I know you covered this early on, but you talked about safe overload, what that means, and will the load cell still meet specs if loaded to 150%?
Yes. Well, it should still maintain meeting specifications within the safe overload. Most sensors will be 150%. Some are more, some might be less. But yes, that's not with frequent use. Frequent use cannot be guaranteed that would be true.
All right, let's go applications.
Sorry, Keith, were you going to say something?
Yeah, I was going to say, depending on what is intended by that question, if you take a load cell into its safe overload zone, but are using it within its capacity, it'll definitely meet spec until you start to damage it. So over repeated excursions into the safe overload territory, you may start to impact the specifications or the performance, but it doesn't necessarily meet published spec if you say we're to calibrate it up to 150% or 140%. So if you're using it up in that range, you're not necessarily within published specifications.
All right,
it's probably not 10 times worse, but somewhat worse.
Yeah, and two things on that. First, every time we calibrate a load cell, we're going to cycle it above capacity anyways. So that's part of our standard process. We'll put it in the rig. We'll run it usually at 120, 130% of capacity a few times. Then we start a cal. So every load cell that we ship has already been over at capacity. Secondly, if you are often getting into that overload range and you can't avoid it, best thing to start tracking would be your zero balance. If you start to see that zero balance shift, then that means you started to do some damage, some permanent physical damage, and you started shifting up that output curve. It may still meet spec, as Keith said, but if you shift it too much, it may no longer meet the spec through the full capacity range. All right, thanks for the questions. Those are good. All right, back to applications. I'll run with this one, I guess, Jeff. So here's a high cycle fatigue test application. In this case, it was furniture testing. Again, most of you probably know how almost every single thing out there gets tested. In this case, choice was an SSMF. There's a fatigue rated S cell, well suited for high cycle testing. In addition to that, it's low weight, so you're not adding a lot of inertial element to your cycle testing. Good safe overload too, 300% safe overload. In this case, it was paired with a 9890, good high resolution 24-bit sensor or instrument, and that even actually takes up to 32-point linearization. So a customer could really dial in that force curve if they wanted to. And again, selectable input range. So if you want to maximize the internal A to D conversion, and using this with different sensors, you can dial in that input range so you keep the most resolution there possible as you may move from one input to the next. Next.
All right, so geothermal well drilling. So customer needed to drill a deep well into earth to tap into its natural heat reservoirs. So the IPCD was a good product for this application. It was, as Brian mentioned before, specifically designed to handle high temperature, high pressure applications. It is highly accurate. We compensated up to 20,000 PSI, temperature compensated up to 350 degrees, and it is a maintenance-free solution. Any more you want to touch on that, Brian?
No, I think that covers it. Next one, all right, animatronics. It's a growing market here. In this case, the customer is looking to add force measurement, multi-axis in this case, to be able to, or excuse me, this is the MRT, so this was torque, to be able to monitor if there's any contact or other parameters to make sure that the animation works as it should. In this case, it offers really high overload protection, which is good. Very good temperature stability. So again, in case this is in an environment where there may be some changes in temperature or exciting things happening, the signals remain pretty constant, and low deflection too, so high stiffness. You don't want a nice soft wiggly sensor sometimes in your test string, depending on the application. And then the instrumentation here, BX8, again, selectable input range. It could really maximize sensitivity and selectable filtering too. It can really be able to dial in the correct amount of signal versus noise. Next one.
So I was to challenge everybody to look up. This is a lifting hoisting application. So aerospace customer wanted to move about to their engine, their aircraft engine safely, to install it, uninstall it. And we went with a couple wireless bow shackles with an industrial base station and a handheld display. Good for outdoor use, up to IP67, made for simple installation and operation. It was proof loaded and fully certified, very low accuracy, or high accuracy, I should say, 1% of full scale, and allowed for long distance transmission.
All right, here's a mooring application. Customer wanted to be able to have submersible shackles. It was hooked up to 9325 portable display instrument, which was very handy in that it could store calibration data for multiple shackles. So you hook up, transfer over to a different one. It would be able to load up the sensor and have that cal data already loaded in there, so they don't have to do any scaling. And the shackle is obviously submersible. So.
All right. Well, an MB load cell was used in this stent and catheter testing for medical application. So the customer needed to apply known forces to the stent and catheters to ensure they pass all necessary strength and flexibility testing. The MB overload protected load cell was selected. We used the DIG USB, good fit for a noisy free environment. MB, proprietary interface strain gauges, NIST traceable calibration, important for the medical industry, and resolution up to 120,000 counts with the DIG USB interface module.
All right, last one we'll touch on today, an example of rocket structure testing. So in this case, we're talking about very, very high capacity and outdoor environment, but still had the need for high precision. So 1200 series is a great choice for that. It's available in very high capacities. We can weatherize it with dual diaphragm configuration and can make sure that it delivers both on the performance and the environmental requirements. And again, with the 1200, you're getting 4 millivolt per volt, so you're getting good signal resolution during that test. All right, so now time for some general tips. So we've touched on a lot of different topics. We've covered a lot of ground on different specifications. The goal is to have everyone come away a little better informed in terms of which specs may matter or where to zoom in. So going back to capacity, it's one that is the start of the discussion. Customers generally may think they've got the capacity figured out, but the reality is it has a pretty important influence on the quality of measurement or the life of the product, right? Is this thing going to survive or not? So really want to make sure that it's properly sized to give you as much signal as you can, but that doesn't have any physical damage. And we actually have composite loading calculations that we can run through if you have a scenario for an LP where it may have a lot of extraneous loads, you can't get rid of it, so we can work through that. And obviously we spec out, as you saw earlier, what our low profile product families can tolerate, and not only tolerate, but also the max error there. Other thing to keep in mind too is what is fatigue rated. A lot of times, a couple 100,000s might be thought to be fatigue rated. In reality, no, that's fine. You can use a standard load cell. Or if you do have a fatigue test, where you are going to be doing millions of cycles, and the load cell isn't fatigue rated, you can often just go up in capacity, or at least choose the right capacity to where you're going to be operating in a realm where the sensor can easily tolerate the cycle count. Especially keep in mind too, if it's single mode. So our fatigue rated load cells, as you heard from Jeff, 100 million fully reversed cycles, right? That's both directions. When you're not cycling and you're not doing cyclic loading, that also greatly reduces the chance of any fatigue risk. So if you're doing just compression only or just tension only cycle, you're likely going to be fine with a non-fatigue rated, especially if you're only operating at, say, 30–50% of that load cell's capacity. So these are kind of good discussions to have with the AEs, the application engineers, to figure out exactly how much capacity you need. The other thing to pay attention to is just because you may find another load cell somewhere else, or you may be looking into, pay close attention to what the signal output is. It is commonplace for some people. We don't do it very often, only I think on a couple products where we'll offer a half calibrated load cell as a specific capacity. Most of the time we try to maintain the same output across all stated capacities. So again, you may be thinking you're finding a load cell that's rated for half the capacity, meaning you're going to have better signal or better measurement, but in reality, you're just getting half the output. So pay close attention to the outputs when you're comparing capacities. All right, next one. So accuracy. We had a lot of specifications that are under that accuracy header. It's really difficult to just assign a certain number, but really it comes down to understanding how in your particular application, which specifications will apply, right? Which ones can you remove, which ones factor in, which don't. It's going to come down to the temperature profile of the test. If it's constant temperature, good. You can move all the temperature stuff off the table. It also comes down to your load profile, like you heard earlier. If you're only doing a single ascending test, hysteresis, for example, doesn't matter. What calibration data do you have? If you have either your specific load point, or if you have the curve data, then you can take out maybe nonlinearity, even hysteresis again from impacting your measurement. So load cells are ratiometric. We mentioned this earlier. Pay close attention to the quality of the excitation that's going to that sensor, because any noise that's coming in on that excitation side is going to now show up in your measurement signal. So pay close attention to that. And again, in summary, sensor is just one line. So we spend a lot of time about sensor specs. That's zooming in on the sensor. Now you got to look at everything else attached to it. Next one. Temperature. We've touched on this a few times. Come back again. Key takeaways there to understand how it affects both zero and span. It's characterizable. You can probably compensate some of that out of your test or remove some of it. We can customize it. We want to make sure any temperature is as homogeneous or consistent as possible around that sensor. And then again, think about the rest of your system. If you can run your whole system up to temperature to see how it responds with no force, that would be ideal. Every single mechanical thread, any mechanical joint, that's going to respond differently to temperature. So even if you zoom in too much on the sensor, you may have other air influence that makes the sensor irrelevant almost. Next one. Calibration. So we could do a whole nother webinar on calibration, but for best performance and best match, you want to try to ensure your calibration is as close to what your actual test is going to be. So do you have tension or compression data? Do you need both? Do you only need one? Like we talked about several times, can you run a multi-point cal instead of just a single full-scale value? And then that's true for the sensor. If you're looking at the sensor specs, what kind of cal does it come with, right? Do you have a multi-point? Do you have a single point? And then the last part too, is it actually, what is the uncertainty of the calibration? So that's usually a separate question you need to have. You can be looking at two data sheets side by side, but if one's got a 0.04% or 0.02%, if it's a dead weight type cal versus an unknown or uncredited cal, it makes your unit measurement a little bit risky there. Last one. So system specifications. So this is kind of the culmination. We zoomed in on the sensor. Really understand the fact that there's specifications for the entire system. So you're going to have your instrumentation. You're going to have potentially cable influence. You're also going to have maybe some influence from fixturing. So again, how we attach to a load cell, how we calibrate, how we can then hit those performance specifications, it's going to be a function of how we're attaching to that load cell. So always want to follow best practices, because if you want to try to get the performance that is specified on a data sheet, you got to make sure you're hooking up to the load cell correctly and that you're utilizing it in the proper manner there. We talked about it before, not all specifications will apply, but through best practice and also understanding from an application standpoint, you can really eliminate most of the specifications on a data sheet, and you're going to be left with 3 or 4 maybe that are of importance when you're looking to select a sensor for testing. All right. Top 10 FAQs. I'm not sure if they're top 10, but there's certainly some that pop up. Jeff?
So what is the most commonly asked question? What is the accuracy? And there's not always a great answer for this, but if we were to provide one, it would be the SEB error. But the accuracy is always going to be determined based on your application, your environment, your load string. So it's a tough question to answer with many factors that go into it.
All right. Well, the datasheet identified the output signal for the transducer. Absolutely. Pay close attention to not only how much signal you're getting, but what is the signal. Make sure you've got the appropriate instrumentation, not only from just pure compatibility, milliamp voltage, millivolt, but also the range. Pay close attention to that.
Why don't I want as much excitation voltage as possible? Well, every load cell has a spec for how much excitation it will handle. You start putting more excitation in there, you're heating up the load cell. More is not always necessarily better. 5 or 10 volts is normally fine. And then it does get into, how much signal am I going to get back? And modern data acquisitions can normally decipher a very low signal, and they've gotten very good. So you don't always want to just maximize the excitation.
Yep. Again, rule of thumb, if it's really small, 5 volts is probably good. If it's normal sensor, 10 volt, you really shouldn't need more than that. So why does the cable matter? So we talked about that. Cable can influence the measurement. It's going to respond to just actual voltage loss as a function of length, but also perhaps more noise susceptibility. Excuse me, what type of cable is important? You want to use shielded. Sometimes you need to do twisted, maybe, depending on the environment. And then, of course, how are you? What about the connector? Interface offers 6-wire cables. So even if your instrumentation doesn't support sense, we will at least loop it back through. Even if the sensor doesn't support sense at the bridge level, we'll still loop it through the connector. And in that way, if your instrumentation supports it, you'll still be able to take that into account. And also keep in mind too, if you buy a standard load cell, you're gonna hook it up to a 100-foot cable run. Please let us calibrate it with the cable attached. We'll be able to make sure that the cal data then is representative of what you'll actually see.
All right, so what are the option codes at the end of the load cell model? Richard Karras decided to incorporate option codes to all of our load cells. Unfortunately, there's no really rhyme or reason, but you might see ACK or AF or AJ, but these define the feature codes within the load cell. So if you get a new load cell from us, you'll know it, but if you find one out in the field and want to know, please contact us, and more than likely we'll be very happy to let you know the option codes or the feature codes within the option code.
Yeah, and we've got the Karras guide up there to address some of the more common ones that are out there. So it's on the website. All right, our bases and mounting instructions included with load cells. Bases, usually if it's an LP, you'll need to specify. Part number becomes a -B. We always recommend bases. That'll help give you your best chance of hitting the specifications of the datasheet. You can still use it without a base. Again, we want to make sure that there's adequate hardness of the mounting surface. And then 2/10,000ths total flatness, as was mentioned earlier. That's what we test ours to, and we can't guarantee performance or meeting spec without. So it's always best. Bases make it a lot easier just to hook up to the low profiles as well. So mounting instructions. Mounting instructions are going to be included. Not included necessarily with the shipment, but they are available online. So we have all the necessary installation instructions available online for that.
Number 7, why is a high-level amplified signal not automatically better than millivolt per volt? Well, millivolt per volt is what inherently comes out of the load cell. When you are amplifying a signal, you are introducing another possible source of error. You're translating that just as if you were adding a mechanical joint in your load string. We don't always know how well the amplified signal will respond to temperature. As the load cells are accommodated for that, the amplified signal may or may not be. So it's sometimes you're going to want that so that you could see a finer resolution, but inherently millivolt per volt will be best.
All right. Do you calibrate all the items together, load cell, instrumentation, cable, same time? We absolutely can. If you order items independently, there will not be any sort of setup. We always recommend a SysCal, system calibration. Nominal fee, and that ensures that the instrument, when you receive it, has been scaled for that particular load cell. Now, most SysCals are going to use a ratiometric scale using a NIST traceable CX box. So it's a fully NIST traceable system calibration on the instrument itself. However, we can certainly calibrate all the items together on the load frame hooked up. That'll remove a few layers of the error budget, if you want to think about it that way. In that now the reported value is going to primarily come down to the uncertainty of our load frame and our A2LA accreditation in terms of scope. So you'll automatically get total system performance down in the 0.04% type range if it's good components that you're using there.
So where can I find the definitions to all the values of the data sheet? Well, you can scroll up. They were covered in most of this presentation. You can also find them on a glossary on our website. And lastly, the field service guide that we publish and offer contains all the definitions as well.
All right. And what is the resolution of this load cell? We get asked that a few times. Really, it's a millivolt per volt analog device. So theoretically, it has infinite resolution in terms of output response from force applied. The reality is resolution is typically going to be limited on the instrumentation side. You're going to be looking at your A to D conversion limit in terms of how your instrument can take an analog signal and break it up into digital chunks. But general rule of thumb in terms of sizing a load cell for a given force level is try to stay above 1 in 30,000. Again, even though the load cell will respond infinitely, that's generally a decent area. Again, assuming you're using some good quality components and you've taken system level considerations into account. So resolution almost always limited by the instrument.
You can use the chat feature if you'd like to ask additional questions while we're on this event. This event is recorded, so there'll be a lot of references that you can go back to as well. I want to share with you a lot of resources that we've put together that are available for you to review online. That includes our selection guides, which is a new series of different tools that you can use to make the right selections in choosing your instruments, as well as your sensors. Our technical support information and troubleshooting has a lot of these FAQs in it. As just noted, our load cell field guide, we've made that free to anybody for download. It's a great engineering tool to have on hand for anybody that is using any type of load cell. We do offer all of our installation guides and operation manuals. Our drivers and software are online. You can find lots of catalogs, lots of blogs, and we also have a lot of industry solutions like the applications that we'll review today. Our webinars are recorded. You will find them online as well as on our YouTube channel. For everybody that registered for this event, you'll actually get a follow-up that will detail where you can find that information with one easy click. So the question that we had before detailed all of that was, can you please go over zero balance spec? Is that used to check if the zero balance on the specific load cell has shifted too much?
Good question. Keith, I'll let you follow up if I don't fully answer this, but zero balance is basically going to confirm how one unit to another unit manufactured might deviate around zero. Okay, so all load cells as shipped will be within that spec. It's not necessarily a spec to use to track potential zero shift. That I would look at the particular CalCert for that sensor, see what it was originally calibrated at, or if you have a receiving at your facility, check it, log it, and then check it the same way over time to see if that zero is changing. So, Keith, is that sufficient?
No, that's good. I'd add that sometimes we'll talk to customers and they say, oh, my load cell failed suddenly, but actually what it's been doing is being slowly overloaded over time. But if they're, say you have a tear button or a zero function in their instrumentation, they may have been zeroing out the zero shift, for a month or two, and then bang, finally it fails. So it is important to track that zero and look at it. And if it's moving out, there's something wrong.
We have another great question. Is it reasonable or precedented to use the hysteresis, linearity, temperature scaling, etc., error data points to process the data after the fact for increased accuracy? He provides an example, making a MATLAB script to process the data based on known error points.
Yeah, it's done to some level. I'm not sure I'd recommend compensating all error influences. You may end up deviating pretty far away from actual. But if you have some extremes, especially with regards to temperature, and you have good confidence that you've been able to characterize the sensor for temperature, then you can certainly do some post compensation that way. That's common in some of the real high, more demanding applications we support. Certain customers do that. If you have the ability to compensate for the nonlinearity, that's what our gold standard software does. If you generated a polynomial, you can do that. I think it's reasonable. Just don't go too far. Keith, what would be your response to that?
I would say the linearities and things are relatively small, so it's easy to do the wrong corrections if you're trying to correct for very small errors. But a lot of systems have maybe a lot more, say, non-linearity in them than the load cell itself. So it can make a lot of sense to correct the entire system. Same thing with temperature, like zero. You could easily cycle something in a temperature chamber with zero load on it and then do a zero correction. Again, once you load it and all the other items are expanding and contracting, you may find that that correction you're doing isn't necessarily valid for the system. So yes, but you need to consider, very carefully what you're doing.
I know we've covered this in other presentations, but we often refer to error budget. Can you guys just give us like a quick description of what you mean by that?
Sure. Well, essentially, it's looking at all potential influences for error. So you're going to look at your sensor, you're going to look at your instrument, you're going to factor in potential influence from misalignment maybe, and you come up with a calculated value. Typically, there's some weighting that's applied, but this is essentially how we followed Pray-2LA to come up with credited scopes of calibration uncertainty on our different load frames and deadweight frames. We might have some content out there on that, Keith, that we've already done. It starts to become a pretty meticulous process, but again, you can look at it from an individual application standpoint and look at the high runners and figure out again which contributors may I have and how much influence do we think we may have. Keith, your thoughts?
I agree. Definitely you don't just add up all the errors. Some of them may not be applicable at all. Some of them you can mitigate. So it really takes kind of an understanding of the exact application and system before you can really do a correct error budget.
I think that's a great topic for a future webinar, Keith.
Oh yeah. All right.
Registration's now open. All right. If there's any other additional questions, please post them here, but as well, all of our application engineers are available to help you make the right selections, address any questions. If you have a technical support question using one of our products, please make sure to outreach to anyone here. We're here to help. Kenny's got one more question. To determine the SEB, is the BFSL calculated on the raw unnulled data, and is the BFSL forced from 0?
So it'd be the raw data because it's taking into account the non-return. However, is it the tiered 0, Keith?
It's raw, as you said, and it's forced through 0.
Okay.
And for those BFSL, meaning?
Best fit straight line.
Perfect. All right. Again, if you have any more questions, I'll wrap this up, and appreciate everybody staying over to make sure that we got all those questions answered. Just as a note, we design, build our products, we test them, we calibrate everything before it leaves. We are known for accuracy, and that's why specifications matter, because we want you to have visibility and traceability on every product that we make, and the details in each device are available online in our data sheets as well as our web pages, but also you'll see a lot of that information when the product ships in our calibration certifications. Finally, just know that it's important for us to make sure that we deliver the right solutions for you. We appreciate your business and the opportunity to serve you for all your test and measurement needs. And again, if you have questions, need us for any further help, we're standing by, ready to assist. Thank you, Brian. Thank you, Jeff. Thank you, Keith, for an incredible webinar. If there are no further questions here, I just want to say thanks to everybody for joining. Your time is valuable, and we appreciate you coming aboard to learn more about specifications.
Thank you, everyone.
Thanks for attending.
Thanks, everyone.